Okay, welcome back. Yay. All right. So here we are. For all x belonging to z, x relates x. And that means x plus x is even. All right. So let x belong to z. Well, if x is even, then so we have to consider both if x is even and if x is odd, right? Because all we know is this. It's an integer, and we know integers are even or odd, so we have to do two cases. So if x is even, then x equals 2 times m for some, you guys know this definition, m belonging to the integers. So x plus x is equal to 2m. That does not look like an m. 2m plus 2m, which is 4m, which is the same as 2 times 2m, right? Okay, well, and actually, you guys are sophisticated. We don't even have to rename the integer. We can clearly see, you guys can clearly see that that's even, right? So we can say, thus, x plus x is even, which means x relates x. Well, what if it's odd? Okay, so if x is odd, then x equals, let's say, 2n plus 1, for some n belonging to the integers. Well, so x plus x would equal 2n plus 1. Actually, we really can simplify this and say it's just going to equal 2 times 2n plus 1, right? Which is even. Okay, so thus x plus x is even. And x relates x. And so we can say, hence, R is reflexive. We'll save the therefore until we finish all properties on the integers. Okay, so we're moving on to symmetric now. And this one is for all x, y belonging to z. If x relates y, then y relates z. This is what we need to show, right? Okay, and so proof is, well, let x, y belong to the integers. Suppose x relates y. Well, what does that mean, right? That means, according to this relation, that x plus y is even. Okay. Well, since x and y belong to the integers, and the integers are commutative. Oh, okay, my stylist is trying to give up on me. Commutative under addition, right? Not subtraction, but definitely addition. Then x plus y will equal y plus x. Thus, y plus x is even. And hence, well, and we could say, so y relates x and R is symmetric on z. All right. And I would suggest, why don't you try to pause and see if you can set up the transitive property on your own, because once you understand the symmetric property, really, because it's conditional, you should understand the transitive. All right, we are back. And the transitive property. Yes, yay. I hope you guys are excited as I am. So we have to show for all x, y, and z on the integers, or belongs to the integers, if x relates y and y relates z, then x relates z. That's what we need to show. Our proof, I like to change the colors. Well, let x, y, and z belong to the integers. Suppose x relates y and y relates z. All right. Well, again, what does that mean by our relation? So that means x plus y is even. I hope you can read my writing because I can. And y plus z is even. Okay. Well, so I can write x plus y as 2p and y plus z as 2q for some p and q belonging to the integers. Okay. Well, what does that mean? Well, what do we need to show? So always keep in mind, what are you trying to show? You're trying to show that x relates z, which means x plus z is even, right? Well, we have these two equations. Let's just add our x plus z together and see what happens, right? Well, x is going to be 2p minus y, right? And then z is going to be 2q minus y. And so that's going to give us 2p plus 2q minus 2y, which equals 2 times the quantity p plus q minus y. And we're done because you don't even have to do that. You guys are sophisticated now. And so you would say, well, thus, because we're talking about integers, x plus z is even and x relates z. And now we can put it all together and say, therefore, R is an equivalence relation on Z. We will stop here in the notes. So you should be able to do some of the homework problems. Feel free to move ahead and finish out, see if you can finish out the notes. I'll do the other part in another video. So this is part 2. The other part, we have quite a few more pages to do, but I wanted to stop here at equivalence relation. So I will see you all in class.